This is our afternoon session here. So our first speaker is Guido Imperiale, software engineer at Coiled, maintainer of X-Array, contributor to Dask.Distributed, and pinned. He's here to talk about active memory management. So stage is yours. Have fun.
Good morning or afternoon, everybody. So today I will talk about how the distributed scheduler manages memory over the cluster and what are the shortcomings that are currently affecting it and how we are going to improve on them as I speak and in the next few months. At the moment, Dask.Distributed has completely automated memory management in the sense that if you have a task on worker A and the input of that task is currently on worker B, transparently, without you needing to do absolutely anything, the distributed scheduler will make a copy of that piece of data, which we're going to call a key value pair, and is going to copy it on worker A so that the task can start. This is great for simplicity. However, there are a few gotchas that one needs to keep in mind. The first one is that before this copy, you had one single copy of the data, and now you have two, which in most cases is actually desirable because the same piece of data may be required on worker B soon, and you won't need to copy it back since you already have it on both worker A and worker B. But on the flip side of the coin, that means that you are now consuming double the memory over the total of the cluster for the piece of data. The other problem is that if you have a Nexus task that collates a massive amount of large pieces of data into and puts them into an input as a single function, then you will get a spike in memory over a single worker, and that spike will not deflate until those keys are released. When are they released? Well, Dask will work in a way that will make them release as soon as possible. It will go out of its way to run the tasks that need those keys as fast as possible. But nonetheless, those keys will stay there for a while, for as long as they're needed. So you may end up with an imbalance where you have this worker that served this task with a spike in memory usage compared to everything else. A third problem, which is separate but also related, is that whenever you do reach a certain threshold of memory usage, the distributed scheduler has some automated mechanisms to automatically pause and potentially restart a worker. These mechanisms today are improvable. They work in most cases, but they can cause trouble and they can cause failures in your computation, and we are not going to iterate upon them. Let's dive into the specific methods and functions that we are going to touch, analyze what the problems are and how we're going to change them. The first method that we're going to talk about is client.rebalance. So this is a method which is invoked manually by the user from the client, and it tells the cluster, look up the current memory usage across all workers and shuffle around data key value pairs until all the workers are homogeneous in usage. This on paper looks great. However, in practice, there are caveats because of this design and implementation. It is fairly heavy to run. Even if there is nothing to do, it's fairly heavy to run. So it's not really designed to be run on a very frequent basis. And it's not resilient when there are computations running. if you have a computation running and you start and invoke rebalance in the middle of it, it's going to be trouble. First, because you may end up with race conditions, and second, because rebalance will take no regard upon which keys is best to move. It will move the largest keys, which is probably not what you want, because you, for example, you don't want to move around keys from worker A, move it away, when that key is going to be used by worker A in a handful of seconds. Last problem of rebalance is that at the moment it only considers managed memory. What is managed memory? It is memory that is actively maintained by Dask in terms of key value pairs, as opposed to unmanaged memory, which is everything else. RAM used by the Python interpreter, Python libraries, C extensions, other Python objects that are not being handled by the cluster. Memory leaks, garbage collector that hasn't run yet, PyMalloc that has not invoked free yet, free that has not invoked BRK yet, which is lower level in the Linux stack. So there can be a substantial overhead there, which at the moment is not being considered when rebalancing. And when that overhead is not homogeneous across the workers, you have problems because the rebalancing will actually unbalance the cluster. How are we going to act? The first change that is going to hit master in a few days is that the performance of rebalance is going to drastically improve, particularly when there are a huge amount of keys overall on the cluster. Right now, the performance is big O of n log n, meaning that if you have 1,000,000 keys, you are going to have 1,000,000 multiplied by logarithm of 1,000,000 performance in terms of time. And that is terrible in terms of for scaling. So we're going to change it to be big O of 1. That is, if you have 1 key, it's going to take 5 milliseconds. If you have 1,000,000 keys, it's also going to take 5 milliseconds, as long as you don't have keys to actually move around. When you do have keys to move around, then the performance would be big O of n to those keys. So the more keys you have, the more you have a linear increase in runtime. But if you run it frequently, the idea is that you're not going to have many keys, which brings us to the next point. We are changing it to become safe to run during computation and efficient. So we're going to fix all the race conditions, and we are going to make it smarter in regards of which keys are picked first. If I'm going to use a key on the worker, I'm going to leave it there. If a key has been used recently, I'm going to leave it there because by the least recently used logic, it's probably going to be used again very soon. After we do these changes, then we're going to implement a daemon that kicks off rebalance automatically every few seconds. The idea being that if you don't need it, it's going to take 1 millisecond every 5 seconds. If you do need it, then you're going to have a much more homogeneous RAM utilization across all your workers. In initial delivery, these will be opt-in so that people can start playing with it and give us feedback. And later on, we will consider moving to an opt-out design so that it's there right out of the box, and the cluster just behaves better in general, particularly for our unexperienced users. Another change that we're going to do to rebalance is to actually make it consider unmanaged memory. So we are already implementing an algorithm that makes it ignores temporary spike in memory. Typically, for example, the heap of a function is heap, of course, it's Python, it's between air quotes. The heap of a function, or maybe the GC, the garbage collector didn't run yet and will run in 5 seconds, ignore that. So you have temporary spikes of unmanaged memory, and you have a chunk of unmanaged memory that has been there for a while. Consider that chunk on top of the managed memory, the Dask key value pairs. Finally, if we want to run it every 5 seconds or so, we need to be aware that that may cause keys to pinball around the cluster because workers jump between donor and receiver of tasks depending on their exact memory usage. So we're going to implement a kind of a dead zone in the middle that to avoid that, where if a worker is within a certain range of the median of the mean, is not going to lose nor receive any keys. A related change is on retire workers and pause and restart. Retire workers is another client method that says, shut down this worker. Simple as that. Move away all the data from it and shut it down. Again, this is a method that works great as long as the cluster is at rest. If you have a computation running, you may have race conditions. This is particularly problematic when you have an adaptive cluster because this method is used by the adaptive controller. Now, when the adaptive controller starts seeing that the pressure on number of tasks starts adding up, it will spin up more workers. That's great, and it will do so in the middle of a computation. However, it will not shut them down until everything is idle again. And the reason for that is that retire workers is not resilient to run while something else is going on. This is problematic if your workload has a huge spike in parallelism at the beginning, let's say 30 minutes, 2000 CPUs. And then you have 5 hours worth of 20 CPUs. This is a kind of frequent situation. And in those cases, the whole cluster will remain up for the whole time. How are we gonna change it? Well, we're gonna reuse the same machinery of rebalance, and we are going to review retire workers. So use that so that you can actually trigger it in the middle of a computation at any moment, shut it down. The adaptive manager at that point will need to be changed to just say it is totally okay to reduce the size of your cluster while you're not idle. Another pain point that we have is the so-called pause threshold, where when you reach 60–70% of memory usage, you end up with the worker stopping to accept more work and deal with what he has now, which is great, except that when you have a memory leak causing that 70% usage, you will end up completely stuck. And that needs to be redesigned again so that pause can, okay, first offload all the worker, all the data, offload all the pending tasks. Okay, I have nothing left going on. I still have 70% memory. Start a graceful shutdown after the, so move away everything that I can, restart the worker, assuming there is a nanny, like the worker nanny that is bundled with Dask or Kubernetes or whatever. Pardon me. And after that, move back in some data. Now that you cleared the process, you restarted the process, you cleared the leak, you can start again with the worker as new. Third and related topic is replicate. Replicate is another client method. What does it say? The user will specify a list of Dask keys of futures, namely a collection, and say, I want more than one copy of this because this data is important to me. This data costed me a lot of effort and CPU time to generate. So I don't want it to disappear if by any chance one worker dies unexpectedly. It can also be used to preempt parallelism, whenever you want, you know already, for example, that that piece of data will be used across all workers. But we're not gonna analyze that now. We're gonna analyze what happens when you are using it for resilience. You do know that occasionally you have that one C extension that occasionally segfaults. Make 3 copies of this important choke point, so that if that one node that holds the original copy dies, you have 2 more. This works great, except first problem. If that one worker dies, you went down from 3 copies to 2 copies, and there is nothing that will bring it back up to 3. That worker is restarted, that's great, but the third copy will not appear anywhere else. You're down to 2 permanently. If the 2 other workers eventually over time die, you're down to 0. Say, for example, you have started some workload and on your Jupyter notebook, and before you leave for the night, you say persist, publish dataset, and replicate 3 copies. You leave, and then somebody else, before you come back to the office next day, runs some experimental code that starts randomly killing the workers. The next morning you arrive and you have nothing, because all the copies of that data were eventually killed with their host workers. Second problem is that, as I mentioned in the initial slide, whenever you have a task on worker A and the data is on worker B, there will be a copy. Now you have 2 copies of the data. And even if you really wanted one, because that was a temporary yet highly consuming piece of data, you have gigabytes and gigabytes of data that it's very quick to rebuild. So you'd rather not be very conservative in terms of how many copies you have. Don't do more than 1 at any given time. And that's something you can know as a user. Third and final problem, on an adaptive cluster particularly, you ask for 5 copies of that piece of data, except that you have 1 worker running, because there are no tasks. And you're just not going to get those 5 copies, because there is nothing right now that spins up more workers to satisfy your request. How are we going to change it? We're going to define in the Dask config a minimum and maximum number of replicas for each key. Let's say 1 and 2. And then the replicate function will let you override that for specific keys. This key is smallish and was very, very expensive to compute. I want 5 copies at all times. This other key is incredibly large, and it takes 100 milliseconds to generate. Again, I want 1 copy, no more than that. Whenever you copy it from worker B to worker A, delete the copy in worker B unless you actually need it there. And again, to do so, we are going to reuse the same machinery of rebalance. So whenever every 5 seconds or so the rebalance daemon runs, it will go through all the keys that have more copies than required or less copies than required, and do necessary adjustments. This means logic that is in common again with rebalance, such as I have 5 copies. Which of these 5 copies is more, and I want 4. Which copy of these 4 is the least likely to cause problems if I delete it? Maybe on 3 of those workers that data is actually needed very soon. Maybe on 2 of those workers that data has landed 1 second ago. On that one worker has been there for ages and nothing has touched it, so it can go. And again, flip side, I want to create more copies, which are the workers that are least occupied. And so that I can put them there and it's going to be safest. Finally, we can change replicate and scatter, which in turn invokes replicate, to dynamically scale up the cluster. If you require 5 copies, we have 1 worker, call the adaptive scheduler and say, hey, can I have 4 more nodes? Bring them up and create the extra copies. And vice versa, if the adaptive controller wants to reduce the size of the grid, it will need to count the fact that something has requested 5 copies of some keys that occupy a certain amount of RAM. So you really can't go below 5 nodes, possibly more than 5, depends on how much data you actually need to store. And even if your tasks maybe require just 2 or maybe 0. Okay, now we are going to have a little live demo. Here we have a cluster with 32 workers running on my localhost. And we already see something brand new here. This has landed in the master branch a few weeks ago, which is the grand total of the memory stored on the cluster. And another thing that has happened recently is that the bars are not solid color anymore, but you have a split between managed memory, unmanaged memory, and spilled memory. Earlier, you just saw the grand total process memory and you had no visibility of the spills. If I go to the workers tab, I see the usual memory column, which is the usual one, that's the total process memory. And then I have a breakdown: managed, unmanaged, unmanaged recent, which is hopefully a spike, and it's gonna either go away on its own, or eventually be resolved in the long term unmanaged, and spilled memory. Now I will artificially load my cluster with a very imbalanced bunch of data. And I'm gonna use a triangular distribution because it's simple, but I could do a spike of any other description. There you go. Now we have, for every worker, we have solid color, which is 766 in this case, megabytes of managed memory, meaning Dask keys and values that I am tracking either through futures on my client, or they are a dependency of futures eventually that I eventually have on my client, or they are published data sets. On top of that, I have a little bit of 65 megabytes worth of unmanaged memory. This is typical for a Python interpreter plus NumPy plus whatever else the distributed worker needs, Tornado, etc., etc. And on this one, which is heavily saturated, I also see that it started spilling memory to disk. And so the grand process I have here, I see also the grand total of the cluster. I have almost 20 gigabytes of managed memory, and I have 2 gigabytes overall of unmanaged memory. This is a very healthy situation, considering that I have 32 processes. If I started having memory leaks, I would see this brighter area grow over time, and that is the cue that I need to start looking at what's going on in my C extensions or in my garbage collector or whatever. And now I will invoke the rebalance function. This is a work in progress, so I'm now going to invoke it from the client by hand while the cluster is at rest. When we will be finished, it will be invoked automatically every few seconds while the cluster is running and serving computations. And voila. Now, this is not perfectly straight. As you see, some workers have some more memory than others. This is by design. We don't want to over rebalance. Namely, as I said earlier, if a worker is within 5% of the mean, don't touch it, it's good. If a worker is less than 30% total occupation, don't rebalance, even if other workers are completely empty. It's 30%, it's fine. If a worker is above 60% in terms of total occupation, don't make it accept keys, because it's already saturated. Even if the rest of the cluster is worse, leave it there for now. All of these thresholds are fully configurable from the Dask config. So I am now going to leave some time for questions.
Great, thanks so much, Guido. There's already one question, or yeah, there's one question in the Q&A section. Is it possible to use persistent storage like local HDD or S3 as part of the replicate functionality for extra resilience?
Not in the scope of this change. However, that makes a hell of a lot of sense as a design. So right now, right now you have published data set, you have replicate. It would make sense to say, I want backing on persistent storage for this particularly important piece of data. Yes. Yes, it makes sense. You can mock something similar at application level by having a feature that stores the data to disk as soon as it's ready. Most of the collections in Dask already do that. 2HDF5, for example, or 2Parquet or whatever. They will just wait for everything to finish, and then as soon as it's finished, store it down. But if it would that at that point, however, you will not have available for a second half of the computation that takes maybe the second part of the night. It would make a lot of sense to have it semi-transparent there, yes, but it's not in the current plans. It's a good idea.
All right, there's another question. How would one set the N workers for a memory of, let's say, 300 gigabytes to avoid the workers eagerly running out of memory assigned to it?
There is no one answer to that because it heavily depends on your workload, on your design, on how your tasks are sized, the amount of data that they require, and how they are, how the graph works. Do you have massive center stars where all the data from across the cluster needs to be collected on a single worker? Or could you manage to have a design that is a lot better parallelized? If you have a look at Dask Array, for example, or Dask Data Frame, all the reductions always run in two steps for this exact reason. A first step, which is a map step, where you have an initial reduction of every chunk in and by itself. And then at the end, you have an iterative aggregation of whatever is remaining exactly to avoid this kind of situations. This is not always possible and not always easy. So you may end up with painful situations where you need a lot of spike memory to deal with your computation. Again, it depends on your use case.
Great. So one last question. What about work stealing? When does this come into play?
Work stealing is something that already happens right now. So whenever there is a worker that has a bunch of tasks queued on it already, that tasks will be pre-queued by the scheduler to the workers when it sees that the worker is not as almost free. It will not wait, the scheduler will not wait for the worker to be completely free. It will pre-queue stuff, start pushing it so that there is no gap for the worker just waiting for a task to arrive. These can go badly when the currently queued tasks take longer than expected. There are heuristics that try to determine, to predict how long a task will take. They are not foolproof. When those fails, you will have a worker that is empty or almost empty, and a worker that has a lot of tasks queued and is not delivering them as fast as expected. So what happens will be a move of a task from one worker to another. All the input data of that task will be copied over. And that is when the automated rebalance would notice that, oh, now you have 2 copies of the same data, but you really don't need them anymore on the worker you just stole the task from, delete it. If it's below the threshold of the redundancy that you asked for.
All right, thanks a lot. So if there are further questions, there's one coming in right now, but we are unfortunately out of time. So I would kindly ask you to move the discussion to Slack. I am sure Guido will be around to answer all of your questions. So I would like to open now the floor to the next speaker. Thank you, Guido. That was a great talk.
You're welcome.